So, hello everyone. Welcome to this introductory module on complex systems in behavior change. We're going to talk about what is the topic of behavioral medicine or health psychology and some basic principles behind how these things operate. So my name is Matti Heino. I'm working in I've been working in the Finnish Prime Minister's office for their behavioral unit called Kettu, and also we've been lately doing this project on behavior change science and policy with Nelly Hankonen, who is also the behavioral team lead in this Citizen Shield project, which is about fighting pandemics. So if you're interested in this, you can find out more in here. And I also have two blogs which outline some of my work here. So to go on with the topic, we need to discuss a bit like what is a system anyway. So we can think about many different types of systems. There are these systems that are sort of built systems, man-made systems, and other things that have been are more a result of a long series of interactions with the environment. And so we can call a system, we can call many things a system. But there is a very, very fundamental difference between the systems you see here. So we can have these mechanical systems, and they operate in a very different way than these more organic systems. So here you sort of have a, the principle is that you use it to lose it. So the more you use it, the more it wanes and the parts get rusty and all of that. Whereas here, if the system is too inactive, of course, too much activity is bad for you, but usually less bad than inactivity. So if you don't use your muscles, you will lose them. And for these systems, you usually, when you get it right once, you pretty much know how to do it again and again and again, and you can tell someone else how you did it, and they will be able to do it. Whereas here it's very, very, very different. So we're talking about these large networks of parts that don't have a central controller, someone who tells them to grow and to migrate and so forth, and which act via this process of adaptation and learning and evolution. Yeah, so another way to say it is that it's going to change, and you're going to need to change what you're doing. So if we think about causes and effects, many people may have the illusion that they are sort of this DJ with a soundboard which has knobs and turns and things that turn and all of that kind of stuff that affect the music, which then affects people's behavior on the dance floor. Whereas the reality in a complex system can be more like this. So you put in some effort and something comes out in the next 10 years or so. And what comes out is affected by so many different intervening processes that it can really render long-term planning, especially the kind they did in the Soviets, for example, impossible, because you just don't have the information about future and what processes are going to be affecting the thing in its life course and the course of its growth. So what we usually observe and what we know about the world is some form of simplification. So we can have this idea about what's going on in the world, but it comes through some sort of a lens or a veil or something, because we seldom can observe reality in its full richness. And if we want to use it in a statistical or mathematical model, and this applies to qualitative research as well, it goes through this sort of mental model or mathematical or statistical model, and we end up with this. So this is a good simplification of this. If the important thing about this is sitting, but it completely hides the fact that the person is reading. So if that is the important thing, you're sort of not well served with the result of your model. And so this is something that Benoit Mandelbrot, who developed the mathematics of fractals, that he criticized people for doing, that they were making these simplifications, and when they made those simplifications, their models of their world did not get the same result, did not show the behavior that we see in the real world. And this confused many people before they realized that there are other ways of doing stuff, and we have been recently getting access to those things in social sciences as well. So this is a paper we wrote about complex systems in behavior change, and we sort of framed this as three different headings. I won't go through them all. I will just showcase a few of these, but what we did was we defined behavior change as a collection of contextualized processes that are specific to each individual in an interconnected system that can have more than linear dynamics. I will soon tell you what that means. So the idea about complexity, complex systems, we already discussed that a bit. The contextualized processes, individuals can, context matters, and it matters a lot. And individuals can really, they might not have the same intervention or the same procedure can have very, very different effects on different individuals based on their life history and personal situation. And we usually try to smooth these contextual things out with statistical models, and but so far it hasn't really gone very well. And these statistical models are usually also linear models. So I will talk about this a bit later. So in a system where you have two processes going on, so we have the blue process and the red process, and time goes towards this direction. So here, these things, this is something you see that you can observe when you use correlation. So when one thing is above its mean, the other thing is above its mean. And you will see this as a positive correlation if you select correlations. And the same thing here. Actually, one thing is going down when another thing is going up. So this shows up as a negative correlation. And then you can have a third situation where there is no really apparent dependence between these two variables, and you might have a zero correlation. But the trick is that these all of these three situations depict the same system, which is built in such a way that these two are actually causally dependent on each other. And so in the beginning of the time series, they go together. At some point, they start going off sync, and at some point, they are completely sort of not going the same way. And this is like one system. And you can imagine if you take a correlation out of this time series, you will see nothing, because you expect a linear dependence relationship when you take correlations. And this nonlinear coupling is more the rule than the exception in complex systems, because there are reasons why living systems need to have these types of dependence relationships. Again, so if you only, if your model only shows the correlation, you will think that, well, this sort of a system doesn't exist, and you don't take it into account at all when you're trying to figure out what you're doing. And another thing about linearity, you usually, one way to think about linearity is that when you put in more effort, you get more results. So more effort leads to more results in a proportional manner. But on the other hand, you can have a situation like this where you put in a lot of effort and you're not seeing any results. And then suddenly things start working out. And we can also, we have all seen the pandemics that where decision makers are at this point of the curve and they're like, oh, there's nothing to worry about. And then boom, there's actually suddenly a lot to worry about. And this is like another situation where this happens is the classical story about the camel, where you load straws on a camel's back, and one straw after another, a third, and so forth, and then you put the last straw, and the last straw breaks the camel's back. So did that last straw, was it somehow super special? Did it contain specialized ninja camel back breaking abilities? No, of course not. It was a process that accumulated, and then boom, you observed something very surprising that you wouldn't expect if you only had this linear mindset. So we can see here, if this is the mindset, then you don't consider possibly important alternatives. So this can also be depicted as tipping points. So let's say here is a person who has just quit smoking, and this is the system. This ball is the state of the system, and here is the smoking state, and here is the non-smoking state. So you can have this person being this system being wiggled around in this non-smoking state until maybe this landscape shifts a bit up, and some random event pushes the person to this tipping point, and then it falls back to the smoking state, which is now very steep, and he has began smoking again. And there are, roughly speaking, there are two types of tipping points. One of them is this what we call B-tipping or bifurcation tipping, where the landscape changes and it pushes the system to a new state. And another one is this noise-induced tipping, where you have some random event, like let's say death of a relative, or divorce, or getting hit by a car, or something that pushes the system to another state. But usually these work in conjunction, and they're not this clear, so they both happen at the same time. If you're interested in finding out more, I recommend this talk from our behavior change science and policy complexity symposium. And I also wanted to show about this thing about interdependence. So this is a normal distribution. You've all seen this before. And so this happens when things are independent. And when they're independent of each other, so you have like, here you have, just showed the number of events is here, the y-axis, and the horizontal axis is the magnitude of events. So let's say that here are very bad events and here are very good events. And because these events are independent of each other, when you have one event, it sort of balances the system out, and the average describes the system very well. So this is the average, and the average is also the median and the mode, and it's very well descriptive of the system. Whereas in complex systems, you usually have this, we talked about the interconnectedness, the interconnected parts. And so you can have like one event that causes something that triggers another event to the same direction, that triggers another event to the same direction, and you end up like this with this domino cascade spreading through the system. And so this leads to something very different than a normal distribution. And one way to exemplify this is the distribution of pandemics. So I took the parameters from this paper and I simulated 100 pandemics. And here you can see that this bar, it consists of everything under 10,000 deaths, because the x-axis is so wide, and you can see that like 80 to 90 or even more of these 100 simulations, they are just very, very, very minor, and under just a few thousand deaths at maximum. But then this is not the full x-axis, and it becomes a bit difficult to visualize. So we need to do something like this. We make it smaller, we move it, and then we make a new axis here. But the problem is that even this is not enough. So we need to break the axis and signify it with this. But you can also, if you want to think about how far the axis would actually go, you can look over your right shoulder and pick a point through the somewhere in the distance. Because in fact, one event in this simulation of 100 pandemics, it produced an event of 1.3 billion. And so this is, of course, a problem because like most of the time when a pandemic hits, it's not a big deal. But sometimes when it happens, it changes the whole world for good. And if you're only thinking about this types of, or thinking about the normal distribution, or thinking about these small events, and you're like, oh well, let's wait and see. It might be too late when this happens. And when you only observed the kind of the normal events, you might have like the average deaths could be like 10,000 or just a few thousand. But that just means that this hasn't happened yet, because when this happens, the average goes up by more than 1 billion. And this produces some difficulties for our lifestyles. Without going more into that, so it's again the same deal. You have, if your model is not, if your mental model is not allowing these sorts of distributions to happen, you might miss something very essential about the structure of the world. And this is just to show that we can actually date these preventive actions, which one of which could be to actually reduce the interconnectedness and detach parts of the global system temporarily and in a way that disturbs people's lives as little as possible. And when we reintroduce independence in the system, we go back into the normal distribution case where you don't have these super extreme events. And this is something that also happens because decision makers, health officers in many countries, and especially in Finland, they prior to this pandemic, they didn't consider this to be a possibility at all, that mask use would suddenly rise to a very high level and also stay up. So this was just outside their mental model. And just to finish up, we very often can't predict precisely like what's going to happen next, but the properties of the system, what are the connections? Is it independent or is it interconnected? It gives us a sense of its resilience, its fragility or anti-fragility, and it gives us an idea of what happens when something unexpected happens. So in this case, you have a system where everyone is connected to everyone else, and this sort of usually leads to the situation where it's going on very stable, continuing its existence until suddenly, boom, it collapses. Whereas in this state, if something happens to the blue square, the thing can spread to maybe these things if it's not specific to blue squares, but these parts of the system stay unaffected. And when it happens, these parts can then act to help out these parts. And you have time to actually react when you see things going in a bad way. So thank you very much. And this was all I had to say for now. And we'll be back next time. Thank you.